one, go.
Alright. Hello AP Calc students. I am going to be running through a quick demonstration on a potter's wheel of solids of rotation. When I was learning this topic, this is what really helped me visualize things, and I think it can make a really good demonstration of the three ways to find the volume of solids of rotation. So first, we're going to be working with this sort of lump of clay here. This can be thought of as a rough approximation of what a quarter circle would look like if it was rotated at about the y-axis. So if you think of the y-axis starting sort of in the center here, and then the x-axis just sort of going out from there, that's a good way to visualize this graph. And I can slice this in half, and we'll see a little, after I do the demonstration, that the picture of the graph will be a little bit easier with the 2D cross-section. So, when you're finding these volumes, what you're going to have to do is you're going to have to be taking a summation of a bunch of disks. So that's the first demonstration, is going to be the disk method. So I'm going to be physically just cutting off a disk from the top of this clay. I cannot do a demonstration of the x-axis, of a solid rotated on the x-axis, just because of how a potter's wheel works. So any of this will just have to be translated later. I would suggest looking in the textbook. So if I wanted to find the volume of the solid, what I'd do is I would think about taking off little slices, something like this. So you can see I've got a little solid here, and if I were to just kind of lay this down, we can start to think about how we'd start to generalize this area in the volume of this little disk, and then we can think about applying that in an integral to the rest of this solid. So to find the area of a circle is pi r squared, correct? So if you're thinking about this, all of this has to be with a y as the constant. So you're going to be setting up your equations to be x equals y, and you're going to have all of your equation stuff onto the y-axis, on the y component, or y variable. So if you plug in a y, what distance would you get for your x? You're going to get your radius. So pi r squared for your area, and that'll give you a radius. So that'll give you the area of this little disk. If you want to find the volume of it, you're going to need to use dx. So dx will be thickness. In this case, because it's clay, I can't get something infinitely thin, but dx will give you, when you do your integral, will give you your thickness. So if we were to generalize this equation and to do, write out an integral, it would be in terms of y, so it'd be like from y equals 0 to y equals 1 or something along those lines. And it would be, and we'd use the equation to get the radius of this, to generalize the radius of one of these disks. Okay, so moving on. We are going to be using the shell method next. So the shell method is basically finding a bunch of hollow cylinders, is a good way to think of it. So I'm going to be getting this spinning again. Maybe get this a little bit more centered. And then we are going to cut off a shell. So what basically a shell would be. So you're just going to have to sort of see it as it goes around. So I'm going to cut down. Ah, shoot. I missed. All right, 1 second. I'll just stitch that kind of back together and try again. It's going to be a little tricky. So you're going to have to bear with me. So let's try this again. So cut down. And then I'm going to cut under it. And because this is clay, I can't really just kind of like pick it straight up. So I'm gonna basically make this a ribbon. And then we are going to lay this out like a shell normally would sit. So I'm gonna take that off and then sort of put it vaguely back together. And that's about the best I can do. So if we have this little shell here, what we need to think about is generalizing this in terms of x. So in this case, we can actually work with x as our independent variable. We don't have to work with y. So if we have our y-axis here and our x-axis running through here, you can see me kind of drawing on the wheel. We need radius, right? So if we were thinking about the surface area of a cylinder, just the outside of the cylinder, that would be 2 pi r, right? So 2 pi to find the diameter, and then pi would find the circumference, and then h. So 2 pi r h. And that would find you the surface area of this solid. And then if you want the volume of it, you need the thickness. So in this case, the thickness is going to be dx. So in an equation, that would look something like on your integral, you could pull out the constants. So that'd be 2 pi. So you'd have 2 pi on the outside, and then you'd have x, which would be your radius, and your height would have to be f of x. So it'd be 2 pi, your integral, and then x f of x dx. And that would give you the volume of the solid using the shell method. Right, great. So we are going to then move on to the washer method, and that is going to require a different lump of clay. This one is a little bit more recognizable as a bowl. I had it under plastic, so it might be a little crusty. So you just have to excuse me for a second while I straighten this out a little. Great. So here we have our washer. Not our washer. Here we have our solid. It's rotating. And we are going to do the same thing that we did with the disk method, which is just cut something off the top. So I'm just going to take my little needle tool and go in. And take it off. Great. So let's lay this out into something vaguely circular. And this is going to work almost the same way as our washer method. Not washer, sorry. This is going to work almost the same way as the disk method, except we have to find 2 circles instead of just one. So we have our outside circle and we have our inside circle. And to find the area and the volume here, we need to subtract our big circle by our little circle. And in the case of rotating about the y-axis, things are going to have to be with y as the independent variable. So that might make things a little trickier. I would recommend starting with x as the independent variable when you're thinking of this, but because of my demonstration, I can't really do that. So we have our y-axis here, and we have an x-axis running through it. So a good way to think of this is if I were to plug in a y value, so at a specific height on our little bowl here, I need to get an x value for this big circle and for this little circle. So for this big circle, I need the radius, and that would just depend on your equation. And so if you're finding this, it would be pi r squared minus pi r squared. And we'd have to replace our r value with the the equation that corresponds to the radius of the two circles, our outside and our inside. So our outside circle has to go first, and our inside circle has to go second. And you can, using the distributive property, you can pull out your pi's, and you can put that on the outside of your integral. So you're effectively left with r squared, big R squared minus little r squared, and that'll give you this washer, and then dx, in this case it'd be dy, multiplied by dy, and that'll give you your washer method in an integral.